Right, good morning. So, we definitely should go to the math review today, but before that, I'd like to talk about something that's equally important, which is your lab number 1. It was released yesterday, yesterday night, but I wouldn't expect you to do anything yesterday, that's okay. What I want to do is to guide you through very quickly about this particular lab. I would say that's especially important because that one is going to walk you through the rodent tool, which you're going to need for sure your programming test and all your lab exercises. I think for the written test, don't be too surprised if I ask you anything that might be related to rodent. You may not have to use rodent per se in the written test or exam, but I might ask you something related to it. So please spend enough time for your lab number 1. Let me walk you through some important stuff you want to pay attention to. So there is a due dates for lab number 1. When I open the PDF on the e-class, I'll look at that together with you. Most importantly, there are certain tutorial videos which are recorded. You will have to study them carefully. And I will encourage you to also take notes. I also made the iPad notes available to you. But there might be certain additional notes you want to take. If there's any part you don't think I explained good enough, come to me and then I'll try to fill the gap. Right? That's really why you want to study the video carefully. And any tip to make it shorter, you can play double speed or triple speed if you want to. I know some students do that. If that works for you, no problem. Okay. If you play just normal speed, it's about 2.5 hours. I already explained that yesterday. I know it's very long, but I promise this will be the longest one you will see this semester. Later on, for lab number 2, 3, and 4, I might still make some video. They are maybe a very effective way to get you started, but I'll definitely make it not this long. It's not really reasonable for your workload. But just for the first one, please, just make sure you finish that properly. So what you got to do is, at the end of the tutorial videos, you will actually have developed a project named Bank. Don't worry, it's already on the lab 1 instruction. The project name is called Bank. What you got to do is to follow what you did in your 2030 and possibly 2011. You have to export the project as a zip file. So what we're going to do is you got to export it as bank.zip. This will be what you have to submit, okay? And if you submit the wrong thing, then you wouldn't get the marks. Please make sure you submit the right thing. And it's not only that you have to just reproduce the tutorial is part of it, and also there are certain problems rather small for you to also think about and solve. Of course, if you really cannot solve them all, that's okay. As we said before, submit your best attempt. You want to attempt as much as possible. I will release the solution after the submission deadline. And then I'll try to maybe discuss certain highlights that you want to pay attention to in the class. Don't worry. But I want you to struggle a little bit first of the material. They're not trivial. And we're definitely going to start with the math review lecture today. And I can expect that we have to go beyond maybe definitely Wednesday and possibly part of Monday next week as well. So just study along, and I make all the slides available there on the site already. You can definitely study ahead. Those are the stuff meant to be reviewed, which means you have seen them before. Maybe without waiting for me to really discuss them thoroughly with you, you can definitely look at them too. That might help you lab 1. Do you guys have any questions, just in general, about lab? Anything about the course? We're okay, right? Okay. Let me go to the e-class and let's take a quick look of the lab, very quick. And if you go to the e-class, you will see lab 1 instruction over here, right? If you click on that, number 1 thing you want to really pay attention to. I'll try to give you some reminder, but you definitely should mark on your calendar. The submission deadline will be Monday, slightly less than 2 weeks from now. So 12 noon, not 12 midnight, please. 12 noon, all right? That will be the submission deadline. You have to make sure you submit using web submit. That's also discussed in the lab instruction. All right, so please make sure you really submit a valid file with the specified name. It's really important. It's also a very nice rehearsal for you for the programming test. For the programming test, we're going to follow very similar format. So you want to practice as much as possible. And if you want to really use GitHub, feel free. There's also some tutorial video mentioned in the lab manual. And learning outcomes, take a look, but we can go over them maybe again once you have seen lab 1 completely. And the current version in the lab space will be 3.7. And of course, that's the latest version. If you want to install on your own, you can also do that. I recorded this video last year. Okay, so I'm pretty sure it's still very up to date, no problem. The only thing you might find a little bit weird is when you log into the remote lab, you can see from the video, you see the desktop right away. But we have already updated our CentOS on the remote lab. What you gotta do is a little bit more mouse click. You gotta go under activities and then search for files, and then you will be able to see the file system. That's the only difference I can see. But anything other than that, please let me know. I'll try to clarify as soon as I can. Do you need to install the rodent tool on your machine? I would say not really. But for those of you who might prefer to work on your machine and possibly to maybe to export the file maybe later and submit from there, that's okay. But I would suggest, since your programming test is going to take place on the lab machine environments, you may just want to use a remote lab to complete your assignment sometimes. All right, I'll let you strike the balance. If you really want to install the rodent tool, it shouldn't be too bad. I included all the resources over here for you. If you need any help, me and the TA will try our best to maybe help you solve the problem, but we cannot guarantee. We'll try our best. All right, question?
That first link, event.org, redirects to the University of Southampton.
Yes. Okay, let me look into it. Since like the link may have been updated a bit. Okay, definitely. Let me take a note. Look at the link of rodent installation. But for now, please use the remote lab. Okay, but once I can find the relevant page, I'll let you know, and then you can also install on your machine. All right, so that's about what you can do if you want to install, optional. And the background and the problem is something you can read over. I'm not going to do that to waste your time in the lecture. You will spend the time with your classmates or just on your own. I will highly recommend you try the lab to begin with just on your own. And once you and your friends actually have worked on your own for a little bit of time, and then you can collaborate. That's okay. Right? That's really what I recommend. And week number 2, which is now, and also week number 3 next week, we're going to cover the math review mostly. We might just be able to start with the first case study, maybe Wednesday, the later part. But we'll see. But what you got to really study along with the lab 1 is the math review. Predicate logic, which we're going to talk about today, and also sets and relations. That one will be a little bit tricky to really get right. Okay, we'll talk about it. And you're going to read a problem about a bank system, requirements document, and etc. That's something we're going to also emphasize once we get to the first case study about how you can specify what's really intended by the customer. In this case, customer is me, right? I'm asking you to do something that I want. And what about the resources? I would say keep the resources handy. You don't need to study them page by page, not necessary. I would say refer to them whenever you want to find certain stuff you don't really have, maybe in the tutorial video, you can search for them. Yes? Oh, you're okay, right? Okay, sorry, I thought you got a question. No worries. And let me see which one might be more relevant for you guys. I think this one, I think the handbook, this one might be more relevant. They also got some more example. All right? But anyway, explore them if you, whenever you need to. And what will be your task? Number 1, you're going to follow the tutorial video and then reproduce what I type on the screen. All right? And of course, you can easily just get what I type on the screen by fast forward and then pause at some page and then type. That's okay. But I really try to put lots of explanation about how things work. I think you really need that kind of concept, unless you're really confident. Again, I'll leave the choice to you. We'll see if you really understand in the actual test. Right? That's where I can tell. All right, so there will be some part where there will be some exercise left to you. You got to fix the model in order to pass certain proof obligation. That's something you will see once you get to that stage. And number 3 and also number 4 are some extensions that you will have to know. You have to solve. Okay. Number 5 over here is about some further references for you. So when we are in the lecture, especially when we review predicate logic and also sets and relations, we talk about symbols that you can write on the paper. But if you want to use the rodent tool, there are certain ASCII symbols that you have to know how to use them. In the actual programming test, we're going to make this particular document available to you, more like a cheat sheets. So do you really need to memorize the common symbols? Strictly speaking, you don't have to. But if you practice enough, you don't have to waste time looking up the cheat sheets in the programming test. Right? Fair? And then the math review lecture is already there, which I'm going to present some part today. And you definitely want to study that along the way. Especially, I think once you get to the tutorial video, you'll very soon see sets, relations, function, etc. If there are certain terms you're not too sure exactly what they mean, maybe you can go to the slide to see if there's anything that's address it. If not, you can wait a little bit until next week when I cover that part. Or just come to my office hour. I don't mind telling you beforehand. Right? And for the submission, so this is about how you can export. Your project is a zip file that's going to be the same formats for your two programming tests, the same format. Just make sure you practice that. And then after that, you're going to upload to the web submit. So there is a link over here. If you click on that, everything will be very straightforward. Just browse to your file system on the lab, on the remote lab, on your local machine, either way, and then you can submit. So guys, again, please submit before the submission deadline. Cannot emphasize enough. And it is noon, not midnight. All right? Noon. Any question about Lab 1? Yes? Yes, we do have lab today. So again, lab attendance will be optional. Me and the TAs, we will be there, actually having some meeting. But if you got questions, interrupt us anytime. And then we can help you right away. Question somewhere, right? Go ahead.
I believe last week you said that the labs are more like participation ones, but then in the lab I saw that I think your program fails to compile or something, that it's
Yes. Okay, good. So that one there, okay. When can you get full marks? Let's get it very clear. You can get full marks for your lab if, number one, of course, you submit. I can see a record. Number two, the file names are correct. That's it. We don't really look at the contents of your lab. We assume that you try your best. So when I say if you got errors, you might get marks deduced. That means in the actual programming test, you don't want to submit something that contains error. I know there could be some slight confusion. Let me write this down explicitly as an announcement, maybe today. But for the lab, guys, again, if you want to get full marks for your lab, number one, submit before the submission deadline. Number two, make sure the file you submit has the right name. The content itself, we don't really check. We assume you did your best. And then you're going to study the solution very carefully. Also, you struggle enough before the submission deadline and reach out for help. Right? I hope they kind of address your question, right? Good. All right, any more questions, please, before we start the review? Okay, let's start the review. And guys, also get your iClicker on your mobile phone ready, right? Not yet. I think let's cover a little bit, and then we can get to the iClicker. So today can be the first time we do it officially. But we're going to do it sporadically throughout the term. Let me just get ready over here. I think I should be good. Okay, good. Let me start a lecture here, review of math. And for those of you who may want to do a little bit of reading, you can look at chapter 9 of the textbook. Right? It's on the e-class that's already made available to you. We don't really cover every aspect that's actually already covered in the chapter here. So we cover just enough so you wouldn't suffer later to understand certain stuff in the case studies. Right? You can think about the predicate logic and the propositional logic will be used in the bridge controller. And the sets and relations and partial function, total function, and etc. They will be used in the second case study, right? You just need, that's very condensed lecture, right? You could have taken a course to really talk about these, but we don't have that luxury of time. We want to cover more case study for you guys to learn. Learning outcomes, what should we review? Propositional logic and predicate logic. Basically, for our definition here, predicate logic would just be some extended version of propositional logic. We're going to talk about two quantifiers. Remember existential versus universal. Right? You may have already still remember the symbol, but we're going to look at that once we get there. Also going to review sets, relations, and functions. I think we'll try to not spending too much time over here. We'll do some example together. We should spend more time over here. I think this is going to be important. Okay? propositional logic, very quick. A proposition is basically some statement you make. It can be true or false, very straightforward. And we have certain basic operands are true or false, basically, right? Constant, true or false. Also very straightforward. And we use logical operators to construct compound statement. So now we need to know what logical operators we have to really support the propositional logic. Do you guys remember what operators we have before I show it? Let me give you one. Negation, right? What else? And conjunction, disjunction, the or, one more. Equivalence for sure, and one more. Implication, yes. I think implication could be a little bit tricky, usually, to understand what's really its meaning. We're going to spend a little bit more time on the implication. Yes, exactly. And of course, the best way, the most precise way to define would be through some truth table. And for the negation over here, it's a unary operator. There's only one operand. We know that the operand can only take two values, so either true or false. So that's why I've got two rows. And you simply flipped the result, negation. Right? That was really straightforward. Also, we got conjunction, disjunction, implication, equivalence, if and only if. So equivalence and if and only if, we don't really distinguish them much in this course. You can consider them as can be used interchangeably. All right? And then, okay, so there's a truth table over here. Okay? And I'm pretty sure you guys know about the truth table. I'm not going to bother you too much. What I will do is, for conjunction, disjunction, I want to talk something you should know, but I'm not too sure. Let's double check. And for this, for implication, we're going to talk about maybe it's different ways for expressing it. That's also very important for you to know. All right, let's take a look. The way I want to talk about, first of all, conjunction, right? You can see for conjunction here, the only way you can make it true is when both operands are true, right? And let me just make it a little bit thicker over here. And for disjunction over here, the only way to make it false is when both operands are false. It's kind of symmetric. And of course, in the case of conjunction, if it cannot be true, if either of the operands is actually false, it will be false. For disjunction, if either of the operands is actually true, then it will be true, right? It's very symmetric definition, right? We're okay, right? So here is my question for you guys. The conjunction and disjunction operators, which we talk about over here, are they equivalent to the and or operator in Java? Are they the same? Yep, you say yep. Okay, no problem. Okay, how about this? Let me just, don't be shy. Any one of you don't think they are the same. Okay, I got two here. Okay, why don't I take your thoughts first and then I'll call you. Go ahead, why? Oh, we're not talking about bitwise. I mean, you may be talking about this one here. So you can see here we got n% over here. What you were referring to the bitwise is just a single n%. That's different operator. Okay, so let me ask you. If I say n%, would you change your mind? Do you think they are the same?
Yeah.
Okay, down to one. You're the only one left. Yes.
All right, so the difference is subtle, but Java's operators are short-circuiting, meaning that if basically you've already figured out by the first one, it doesn't evaluate the second one. So if I do like true or 1 divided by 0, because of Java's short-circuiting, there wouldn't be a divide by 0 error.
Wow. That's fantastic answer. Okay, so guys, it's okay to be wrong. It's a very common misunderstanding. To actually understand the n% in Java is actually equivalent to the conjunction over here. They are not the same. Very good, thank you. But I'm going to just repeat again, just for everybody. Okay. First of all, you want to understand this conjunction over here is from the logic. It's like a logical operator. And this n% over here is a programming operator. Okay? And what else? You want to see, when I say programming operator, that means you have to consider what's going to happen at the runtime. So runtime execution is a very important factor you have to also consider. And what your classmate, your name? Adrian. What Adrian just mentioned was there is a keyword over here that we have to recall called short circuit. Okay, short circuit. That's something hopefully your professor actually taught you maybe back in 1021 or 1022 or 2030. I hope. If not, now will be the time to learn. Short circuit effects is a way to deal with the logical operator correspondence in a programming language, okay, in the following way. Let's talk about ampersand first. If I have some expression E1, I have another Boolean expression E2. If I put them together, I want to evaluate. At the runtime, of course, the entire thing is actually going to return either true or false, right? So here's the thing. We know that logically, the only way to make conjunction true is when both operands are true. At the runtime, people try to do things a little bit more efficiently. If I already know E1 is false, logically, is it even possible for the entire thing to be true? Not really, right? Because one of them is already false. In that way, is it really worth the computational resources to evaluate E2? Not really. So there's a little bit rationale behind. Okay, I'll write it down over here. The short circuit for conjunction goes like this. If the left-hand side of the ampersand evaluates to false, it would skip the evaluation of the right-hand side, E2. I can just say right-hand side maybe, left-hand side and right-hand side. Symmetrically, if E1 evaluate to true, logically, if we got true over here, then whether or not the final outcome is true or false depends on the evaluation result for the second operand. In that case, we definitely have to still evaluate E2, right? So the short circuit for ampersand, the AND, happens if you actually got the first operand evaluated to false, in which case you can skip the evaluation for the second one for efficiency. However, logically speaking, you don't really distinguish between E1 and E2 being evaluated or not. Usually you talk about, okay, this one should be true, and possibly this one is true, and then I will figure out what should be the result. So it's different. So the difference is, in the logical operator, you basically talk about truth table of all the combinations. But for programming over here, you want to think about what's going to be the result for the first operand, because evaluation is from left to right. And then depending on the first operand being true or false, you may have to determine if you want to evaluate E2 even. All right, that's the difference. Guys, is that clear about the difference? Yes? Mm-hmm. So here we're just assuming that E1 is a Boolean expression. E2 is also a Boolean expression. So we're saying that when you want to evaluate this operator at the runtime, you evaluate E1 first. And then if it is false, you don't bother with E2. If it is true, you have to bother with evaluating E2. That's what we're talking about. The result will be the same in some way, yes, that's true. But I'm just saying that the way you should think of how things get computed is different. One is more about evaluation concept, right? For short circuit, just also remember the evaluation at the runtime is from left to right. From left to right, all right? So that's the short circuit for ampersand. What about the short circuit for the OR operator, symmetric? Let me just write it down. So we also got the short circuit for the OR operator. Let's say I got E1 or E2, all right, over here. And let's say if E1 over here already evaluates to true, right? If this already evaluates to true, according to the table over here, you can see if true is already here, it doesn't matter what the second one is. The result will just be true, right? Agree? Okay, let me write it down. So you really want to look at the truth table to see how they actually develop such a runtime rule. If the left-hand side, oh, sorry, let me still use purple. If the left-hand side evaluates to true, you're going to skip the evaluation of right-hand side. All right? If this is happen to be true, then overall, the result will just be true no matter what. So you don't need to evaluate it. Yes, go ahead.
So the answers are both exactly the same, but the difference is the evaluation.
The evaluation. You can think about conceptually for logic, you have to really evaluate both. You don't really have a notion about left to right evaluation. But for the programming, you do. Yeah, that's what I really meant to say. Yeah. Oh, guys, so I'm not sure if this is really what you did. Usually for programming, I'll just give you one example right away. So for your short circuit effect for, let's say, conjunction, right? I mean for the n%. If I do something like this, whenever I want to get access to my array at index I, right? It's a very recommended practice. Every time if you're trying to use I, some expression value to index into an array, you better check to see that I is actually valid index. Okay? So let me write a separate page to show to you, to be more complete. Okay, that'll be the final example for this topic. So let's say accessing array. Let's say what I want to do here is A at index I. Or to be more general, you can think about here could be some expression E, where E evaluates to be some integer, right? Let's say I, just to be simple, okay? Let me show you the correct solution. And then I'll give you one little bit tricky exercise to do, okay? Let's do the correct one. In order for me to know, oh, by the way, in case you forgot about how array looks like in Java, right? It looks like something like this. Indices start with 0 all the way to a dot length minus 1, right? Just in case, right? So what I need to make sure, this I over here cannot be too small. It cannot be negative. Also cannot be large, too large. It cannot be larger than or equal to a dot length. Agree? Okay, so what I need to do, the correct solution is to write something like the I should be larger than or equal to 0. And also, I should be strictly less than a dot length. Okay, let me move that a little bit. Okay, now, so we are using this conjunction operator or AND operator twice because we got 3 operands. 1 here, 2 here, and 3 here. You can think about this is the expression which we want to guard, protect. The expression to protect. Protect, for example, array index out of bound exception. Okay? And these 2, 1 here and 1 here, these are the so-called guarding condition. Let me briefly walk you through about how this can be evaluated and the different circumstances at runtime. Let's do one exercise together. Okay? At the runtime, it's going to evaluate from left to right. So the maximum number of expression you will have to evaluate will be 1 here, getting true, and then 1 here, getting true, and then you got to evaluate this. If this one over here is already evaluated to false, meaning that you're passing some value that's negative, in that case, you don't really go ahead to evaluate these. You just return false, basically. All right, let me write down here. So let's say number one, if I is, for example, equal to -2, apparently that one is invalid. Right? You think about this is expression 1, expression 2, and expression 3. Okay? If I is simply -2, -2 larger than or equal to 0 is going to be false. So you only evaluate 1, and then you skip these two because it's already false. Right? You don't really allow I to be used as an index. That's a critical point. All right? So that means 1 evaluates to false. 2 and 3 will be skipped. Overall, logically, the result will just be false, right? Because one of the, like a P and Q and R, and P is already false. Doesn't matter what Q and R are. Let's see one more case, and then I'll give you one exercise. What if, let's say, I equals, let's say here, let's make the assumption. Let's say A dot length is equal to 10, right? Let's make that implicit assumption. Let's say the array is of length 10. If I is let's say equal to 12, right? It's obviously, that's wrong. And now what's going to happen at the runtime? From left to right. 1 here, 12 larger than or equal to 0 is true. That means we have to continue to find out more. And 12 less than 10, which is its length, is false. So we don't even bother with this. So we are still guarding this expression here properly. All right, good. Write it down, and then I'll give you one exercise, and we'll talk about it. So here, 1 evaluates to true, and 2 over here evaluates to false. And number 3 over here, it will be skipped. Overall, the result will be still false because one of the operands is actually false. Okay? Question? Here, doesn't really matter. Good question here. So here, do we assume any value of the elements in the array? No, it can be anything. So here, we're only talking about how to guard that particular indexing expression. So it doesn't matter. It can be an array of objects, an array of integer, doesn't matter. Okay, good. All right, guys, question for you. I'll put it down here. Exercise. We'll do together. Assume A dot length, let's say 10. All right, that's something you're already familiar with. And let's say the following expression. Let's say the following. We can also assume we got integer array A, right? Would be something here. Okay, the content itself, we don't need to worry for now. Let's say AI, let's say is larger than 10.
Is that I less than A dot length?
Sorry?
Okay, AI, is that I less than A dot length or J?
AI, we don't have J. We only got AI. We only got I. You can assume that I is some variable somewhere.
No, but okay. It's I that's less than A dot length, right?
Sorry, what do you mean?
You have something is less than A dot length, and AI is greater than 10.
So I can be arbitrary over here. We're just saying that you write a piece of line of code, and then we are now, let me finish that, and then I'll ask the question. All right?
Okay. No, I'm just asking what the variable, what the name of the variable less than A dot length is.
No, this is an expression. You say I strictly smaller than A dot length.
Yeah, that's what I was asking. I was just asking it and making sure that this is the same I as there, but a little like a J. Okay.
Oh, that looks like J? Oh, sorry about that. It's definitely I. I don't mean J.
Okay.
All right? And then I larger than or equal to 0. All right, let's say you write this line over here. Somewhere could be some if conditional, the branching condition, right? So now the question is, does this properly guard? Properly guard AI. If you say yes, you got a disorder scenario. If you say no, you have to give one witness. And hopefully we'll get to universal versus existential quantification. We'll talk about proof strategy. But let's just talk about intuitively. If you don't believe that's the case, give me one counterexample where it cannot be properly guarded. Go ahead, please.
I don't think it properly guards A of I because suppose if I is a negative number, if I is -1 or -2,
Yeah,
then it will go through the first condition.
absolutely.
And the second condition is,
Yes. Thank you. I got it. Thank you. No, over here, let me write it down and then I'll tell you what you should know. No, a witness will be if I is simply, let's say, equal to -2. In that case, -2 is going to pass this one here, right? -2 is guaranteed to be strictly less than the length, which is guaranteed to be larger than or equal to 0. That will be true, so we're still going to evaluate this. -2 will be used as index over here. So you're going to run into array index out of bound exception, right? So what's the problem here? So this kind of shows to you, again, difference between logic and programming. Logically speaking, you want to evaluate all these together. And of course, here you may have to prove certain site condition to make sure I is valid. But in programming, if you place the guarding condition in a different way, you may just run into crash. But if you actually move this to the front over here, like what we did in the correct solution, it's going to be fine. So that's the main point I'm trying to make. So order does matter in the case of a programming operator, not for the logical operator. Okay? Witness will be -2, right? Are we okay with this? Okay? And I have some suggested exercise for you. You can try further exercises. Try other ordering of the guarding conditions and try to see if they works. You want to think about the different combinations and try them out. Okay? And apparently for this one over here, this one will be evaluated too late. Too late to evaluate for guarding. All right? Okay? Any question about this topic here, right? Conjunction here, disjunction here, itself are very straightforward. If you think about Java in isolation or logic in isolation, but if you put them together, it's a little bit tricky. You want to know exactly where the difference is. That's why I'm talking about this. Okay, if no further questions, I will try to move on. Okay, let's talk about the next operator, implication. Right, for implication, to write it, of course, you know the symbol here, like a double line arrow over here. You say P implies Q. It's a very important logical operator. Later on, once we start our case studies, we're going to use a system called a sequence calculus. Don't worry, I'm going to introduce it later. But the logical foundation for sequence calculus is really based on implication. Right? That's something you will have to know later. So P implies Q. And the P over here, different names you can use. You can say antecedents, assumption, or premise. Okay, either way. For Q, it will be consequence or conclusion. Right? We might use either. Okay, that's fine. And then now, how do we understand the truth table for P implies Q? Let's talk about it first, and then we will see if there's any special case we have to worry. Okay? Let's say this. And the analogy I like to use is about a contract. Okay, I'll put it here. Let's say if we got P implies Q, right? That's how you write it. And let's say the P over here indicates, let's say, the salary. Paid, and also the Q over here represents the jobs done. Okay, let me just double check I put it right. Yep, good. And more generally, you can think about here, this is more like the obligation that need to be satisfied. Okay, over here, that's more like, you can think about like the duty that's assumed on somebody, or maybe the benefits you can get, right? You can think about for the university, they pay the faculty member to actually teach, right? So the jobs, if we teach our job, is part of our duty for sure, is also the benefit for the university. Right? You can definitely think of other examples. Okay, let's say this is what we have. And the way to understand the truth table is to think about like a contract. There's a contract between the employer and the employee, right? The employer promise the employer, employer guarantees the employee, they're going to pay them the salary. In turn, the employee must do the job. So we want to think about whether or not this particular implication is true, is going to indicate whether or not the contract will be honored or breached. Okay, let's talk about different cases. Simple case, if P is true, and also Q is true. This, in some ways, is the simplest case. That means university pay the salary and professors, they teach, right? Good. It's a win-win situation. It's honored, for sure. So that means in that way, that will just be true. And let's talk about another one. How can the contract be breached? Let's say the university does pay, but somehow the professor run away. Right? They don't teach. In that way, of course, they have breached the contract. Right? That's also easy to see. Right? I would say these two are the very straightforward cases. The next two is a little bit weird. In that way, let's say here, if the university doesn't pay, that means the obligation itself is not even fulfilled in the first place. In that way, in some, it's really up to the professor. Either they want to teach still, or they don't. If they do either, it's not considered as breaching the contracts. So the contract will still be honored. Okay? False implies true, and also false implies false. Both of them will still be true. So intuitively, you can think about, over here, this is about obligation not fulfilled. Not fulfilled. And this part over here is saying the contract will just be honored, or contract is not breached. Let's put it that way. The contract is simply not breached regardless of the job being done or not. It will just be honored over here. It's a very intuitive way to think about things, just in case you forgot about the truth table. Of course, you can memorize it if you want to, but I would suggest think about some analogy, and this will be some example one, I would suggest. Okay? Guys, any question about this? We okay, right? All right, let me move back to the slide to see if I missed any point there. I think we are good. Okay. Yeah, I'm just using a little bit different turn over here. Yeah, let me just follow what I put on the slides. Okay, you can think about this one over here. I'll fix that first. Okay. I'll fix that first, and I'll switch to that. Okay, so that's the promise. Just give me 10 more seconds. Okay, good. Yeah, so here I'm just using the promise terms and also obligation. They're informal in the Notion, so I just changed my notes slightly. Okay, so everything I said is still valid. Okay, so we promise the salary to be paid, and also obligation for professor will be to get a job done. The same. All right, and if the promise term is simply not really fulfilled, in that case, it doesn't really matter if the obligations are fulfilled. In which case, the contract is simply not breached because the promise term is not there. Right? Just the same. Okay. Let's see anything. Okay, that's about it for implication. Any question about this? And I would say you want to definitely pay more attention to these special cases. When we try to prove certain sequence calculus, or maybe, especially for sequence calculus, there will be some cases it will be trivially proved just because the antecedents is simply just false, in which case we don't need to prove anything. It's automatically proved. Right? Just remember. Right? That's something we'll definitely run into. Okay, implication, and then the next part about implication, for completeness, we want to learn about different but equivalent ways to express P implies Q. Okay, let's go over one by one. And all of them are equivalents, but you want to pay more attention to how we place the P and Q. You may have heard about all of them in your logic course before. You know what? It might be a nice time to maybe pause a little bit, take a break, and then we'll continue with this. How about that? You can get your mobile phone, mobile device, and I would just need to do some very quick setup. It will take me maximum 1 minute. Get your device ready, and then we'll do it. Okay, 3342, view the course. I'll try to do this next time before class if I can remember. And let me just delete a record from last week, right? That's not official, just to avoid confusion. That one we shouldn't need. And today will be the first time we do it. Settings. And I need to go to attendance. I need to refresh my location. Allowed. And should be within 100 feet, hopefully. All right, save. Let's now go to 3342. I'm going to start a class, and then I would just need to, okay, there we go. I'm going to start a poll. You can get ready to check in as soon as I do that. Okay. Either option, A, B, C, D, E. Okay. So now, here's a rule, guys. So if, for whatever reason, you cannot really check in, what you want to do is come to the podium right away. I have a sign-up sheet over here for you, in case it doesn't work. Everyone, it's working for everybody? Okay. Any concern? Once I end the poll, that's it. No argument, all right? Stop that. Done. Thank you. It's now 12:20-ish. Why don't we take a 3 minutes break? 12:23. Don't go too far, and then we'll come back. Hi.
What's the definition of the equivalent to? Because I just checked online, it says that for all the modules, the truth value are the same, then two things are equivalent.
Equivalent, you can think about, you're comparing, let's say, two Boolean expressions. You're saying they are equivalent if they evaluate to either both true or both false.
Yeah.
It's easy as that.
Yeah, so because the question you are asking is like if these simple are equivalent to the so in the question you are asking like these or these are equivalent to.
Yeah, that equivalent is more. Yeah, it's not exactly a logical, question there. Just basically, when I ask you, two things are equivalent, right? Think about just in English. If I ask two things are the same, we just argue if they're the same. If there's any subtlety, they are different. The way they work, of course, they are not equivalent.
Because I am thinking about the equivalent. I'm talking about the truth.
Yeah. For that one, you don't need to worry about truth table. You don't need to.
And also, I think maybe can we use something like in the example, can we use something like this so that it can show that the order does matter because it will change the value of I?
That's a good question here. That one I haven't thought about, but you can definitely think about it because that one there is to say you want to definitely use the value first in the increment, right?
Yeah.
So
because in your example, I didn't see the difference because it won't affect
Yeah.
anything. It
Yeah.
just give us a true or
yeah, so
false.
I suspect this one here, if you got any other expression after this, then this I value will actually change before you do that next evaluation. Yes.
Yeah, so I'm
Yeah.
just confused because if we don't have this one, the order doesn't matter.
I cannot talk about every scenario, right? So I just talk about in principle. And when you actually got the actual problem, you got to judge. Right? Good. Yes, quick.
Enrolled in this course.
You're not enrolled just yet? The wait list?
I'm not. The thing is, I'm trying. I don't have the GPA requirement.
Oh.
For this course. But the thing is, if I don't take it this semester, I'm pushing my graduation back by.
I see what you mean.
2 years, right?
So I cannot really decide whether you can enroll. So you need to maybe speak to the undergraduate office.
So I'm already in conversation with the Vice Chair Jean Cheng. So let's see how that goes. So is there anything that any advice or anything that I should look out for?
Okay,
I
let's
really need this course.
sure. Let's talk outside. Let's talk outside maybe after class. Okay. Yeah.
That's why I came to.
Okay, sure. We'll talk. Yes, something quick, please.
Yeah, it's could you post the for any in-class or in-person exam? Could you post the time slots, start and end time? Because
Oh yeah, for sure.
students with accommodations, you need to book 3 weeks.
Oh, absolutely. You know what? Actually, for written test and programming test, if you for students who need accommodation, they will still take in the Williams Small Center, but their extra time will be set properly by me. So you don't take them in the accessibility like off center. You don't do that.
Okay.
Only the exam you have to do it there. But
Midterm or final?
only the final exam.
Only the final exam.
So for the written test and also the programming test, they will all take place in the Williams Small Center.
Okay, and I don't need to book anything.
Then nothing you need to do. Nothing.
That's perfect.
Yes.
Thank you.
All right, good. All right, gotta be quick, please.
I wanted to see, because I took this course last year. I didn't pass. But for this year, I want to take 4315, but they're not letting me.
Okay, let's talk maybe outside. I know it's a little bit inside. I can tell you. Let's talk outside, maybe after class. All right, guys. Let's now get started again, please. Okay. All right. So the next topic here. Let's now talk about different ways to really express P implies Q. Okay. Could be a little bit confusing, but it's just how people will talk about different ways, but what they really meant can be boiled down into P implies Q. All right? Let me give you a little bit look ahead, right? When you say P implies Q, instead you can say Q if P, number one. I'll explain one by one in a moment. You can say Q if P. That's really the same as P implies Q, the same. That's one. Number two, you can say P only if Q. And notice one thing. The order Q and P and Q, they're different, right? So you're going to really work out, maybe after, within the class, I'll try my best to really show to you the correspondence on the truth table. I'll try to show to you. But after the class, you got to make sure you really get convinced on this, okay? Second way, you can also say you can also say P is sufficient for Q. Number three. Number four, Q is necessary for P. Number five, Q unless not P. Okay, so let me give you an overall message over here, and then we'll talk about one by one. If I give you something like a P implies Q, of course, P can be some compound expression. And Q can be another compound expression. And then I may just ask you, which of the following will be equivalent to this P implies Q, right? One will be Q if P. Second one, P only if Q. Third one, P is sufficient for Q. Fourth one, Q is necessary for P. And fifth one, Q unless not P. And what I typically like to do, I might just switch the order, right? I might just ask you, is Q is sufficient for P? Is it equivalent to P implies Q? Absolutely not, right? So that's why you got to be very clear about definition. I might ask you Q unless P, in which case they're also not equivalent because I get rid of the negation. Okay? So you really want to understand. Memorizing might get you survive on the written test, but in the exam, I think you got too much other information to worry about. So you may just not want to just memorize. Just want you to understand what's going on. Let's go one by one. Okay, the first one here is Q if P. So this one is straightforward. Q is true if P is true. Over here. Okay, let me try to get here. So Q if P over here. So that means for the implication of, so Q, okay, let me show to you here. Okay, a summary quickly. One here and one here. These two can be considered in a very similar way, these two. And also this one should be considered separately. And these two can also be considered together in a similar way. So that's why when you study the notes, you will see. Okay? And let me just look at this one first. Q is true if P is true. Let me write it down and then see how we can see from the truth table. If P is true. Okay? Let's now take a look. That one is really easy to look up over here. Q will be true, and then P is true. So this means the whole implication is actually true. This tells you that this particular causal relationship is satisfied. If we know that P is already true, then it's got to be the case that Q is true, so that the whole implication can just be true. All right? On the other hand, if this is actually true, but this is actually false, the causal relationship is not really satisfied because this one does not imply this, then the whole thing will be false. Okay? A little bit similar to the contract that I just mentioned. Okay? And when this one over here, more like a condition or premise, is simply not true, then we don't care what this is. Okay? It will just be true anyway. Could be a little bit tricky over here. If P is not true, no guarantee what Q is. Okay, that's the first one. Okay. Okay, and we'll get to the P is sufficient for Q a little bit later. Okay. And P only if Q. This one a little bit even trickier. Let's see, some explanation here. Let me read it first, and then we'll look at the truth table. If P is true, that's something we know. Then in order for the entire implication to be true, the only case for that happen is for Q to be true. What does that mean? Okay. If we know that, so we really have over here, let me just make sure I'm talking about the right one. P only if Q, right? That's what we are talking about. P only if Q. If I know that P is already true, right? Then the only way for the entire implication to be true is when Q is also true. The only row we have that will satisfy this is just this row. On the other hand, you can see when P is actually true, but now we don't really have Q being true. In that way, P implies Q would just be false, right? Okay. So what you really want to study for is maybe about this insight, which I summarized over here. Okay. And similar idea as before, What if P we know is already false? In that case, we don't really care what this is. If we don't really care, then there's no violation about the implication over here. That's why they still remain to be true. Okay? Similar. P is not true, then simply don't care. All right? That's the second one. Okay, so now something you guys also learned from the previous logic course. If you actually want to prove something that's a P equivalent to Q, then what? Well, you prove the P if and only if Q, right? That's how you pronounce it. So what are we really proving? Let me write it down over here for you, and then just make sure you're fine. Think about this. In order for me to prove P if and only if Q, let's say, I want to prove two things. I want to prove one way P implies Q. The other way, Q implies P. First of all, right? And once you study over the terminology over here, you're actually going to see. This one here, how do we call that? P only if Q. I just want to make sure I don't really get it right. And the second one would be P if Q. Right? So that's something you have to remember how to prove. Right? So maybe sometimes I want you to prove this one here, but I say I only want you to prove the only if case. So you will have to know what I ask you to do is to prove the P implies Q case, but not the other one. All right? A little bit dry, but that's the definition you should really recall from previous one. All right? So these are the two I just mentioned. The next one. P is sufficient for Q. So for this one here, you can consider that just the same. P is sufficient for Q is really the same as Q if P. They're really the same. If I know that P is already true, it's really sufficient for me to know that Q is also true, so that the causal relationship is actually satisfied. Okay? And the don't care case also followed. Right? It's always the don't care case when the P is actually false. And here, Q is necessary for P. This one here, you can see it here, it will be the same. Okay, so Q is necessary for P. How do we interpret that? If I know P is already true, the only way for this one here to be true, it would be necessary for Q to be true. Okay, that's how you interpret that. Okay, I'll write this down here. If P already true, for the entire implication to be true, is necessary for Q to be true. All right, that's how you interpret that in the truth table. And on the other hand, you can see P is already true, but Q is not true. So that means here, the necessary condition is not there. So that's why it has to be false. And we also got the don't care cases. All right. Finally, Q unless not P. And for this one here, I gave you some explicit hints. To think about the way to interpret this is to look at when will we get true value for the implication. Okay? Okay, so here, you can see we got true over here. Let me just give you here. Okay, let's look at this. When can we get true value for this? Let me just highlight in a different way. This is one condition for the implication to be true. And why is that? To see this one here, you can see when Q is actually true, the corresponding value for P implies Q is simply true. That's what this Q really means over here, right? And you can see when Q is actually true, doesn't matter what P is. The result will just be true anyway. So that's this part over here. Unless it's just another condition you can satisfy in order for the implication to be true. What is that? Not P. When it is not P, that means P is actually false. In that way, you can see when P is actually false. Over here, you can see both these two are also true. So here you can think about Q unless not P. We're basically talking about 1, 2, and 3 rows where we got true for the implication. It's either when Q is actually true that we get true over here, or when not P over here that we can also get true for the implication. The only case that's left from here is when we get true implies false. And this one will be the only case where we got false for implication. Right? So this one here is the only one you have to look very closely at the truth table to look up the different cases for true. All right? So that's the only case that's false. I know dry could be confusing, but any question you want to ask, I can try my best. Otherwise, study this a bit, and if you got more questions, I can try to answer. Okay? But that's something you guys should know. That's from before. Let me move on. Okay, so for implication, there are certain terminology you also need to know. We talk about inverse, right? If I got P implies Q, let me try to summarize them over here. We got three things. We got inverse, we got converse, and we got contrapositive, right? So these are the three things you can actually, we're not saying that they're equivalents, but these are the different variants you can actually draw from the implication. Okay, the first one. Inverse. Okay, if I given P implies Q, number one, it's inverse. Oh, sorry, thank you so much. Please, thank you so much. Just let me know whenever I forgot. Inverse will be not P implies not Q. Okay, you basically just put negation to this and to this. And by the way, inverse is not equivalent to the original one. You can feel free to do a truth table to show that. Okay, number one. Number two is something called converse. Converse would be just Q implies P. You don't put any negation. You simply just swap the order. Q to here and P to here. And inverse is not equivalent to the original one. Converse is also not equivalent to the original one. Okay, the final one is called contrapositive. Contrapositive. One way to think of it is it's the inverse of the converse. What you can do is, first of all, I want to take the converse, which will be Q implies P. And then if you want to take its inverse, you have to put negation. So not Q implies not P. Right? And you guys may have learned about certain theorem before, right, in 1090. P implies Q is equivalent to not Q implies not P. Right? That's a well-known theorem. Of course, you can use a truth table to prove it. What can be a typical question I might ask you in the test? I might give you something like this, for example. Let's say I'll just write something down on scratch. I'm thinking on my feet. So let's say if I got something like an x larger than 3 and how about this? Let me do it again. Sorry. Now I got it. Let's say x larger than 0 and x less than or equal to 10 implies something like y larger than or equal to 3 or y strictly less than 5. Okay, let's say I just want you to do symbolic manipulation. Let's say this is given. Can you now try to work out the inverse, converse, and contrapositive? Also, apply the so-called De Morgan when necessary. When applicable. Right? That's some exercise for you. I'll try to go over the answer with you maybe next time. Right? You can give it a try. And in case you wonder about what's really De Morgan, it's actually mentioned in the next slide. Okay? That's an exercise I would suggest you try. That's a very simple one just to test your knowledge about the definition for 1, 2, and 3. And make sure you use De Morgan if necessary. Okay, next one. And we got some axiom over here. Let's see. After this, we got predicate. Okay, very good. Let's go over the definition very quickly. Definition for implies, you know, P implies Q is equivalent to not P or Q. Right? That one's easy. I'm not going to bother you. And we have something called identity. That's really interesting. In the slide, I'm only listing the identity of implies. But we do have identity for conjunction and disjunction as well. Okay, let me write it down first. Okay, identity. Okay, make sure. Identity. Okay, so what we got for you is P implies true. Let's just make sure I wrote it down correctly. Oh, beg your pardon. Absolutely. True implies P is equivalent to P. What does that mean? If you got the antecedents already being true, then the truthfulness for the implication depends on P. If P happened to be true, the entire implication will be just true. If P happened to be false, then the implication will just be false. So that's what called identity. So you can simply simplify P into itself, basically. So now, do you know what's the identity for conjunction? Basically, I want you to do some fill in the blank. Something and P is equivalent to P. I heard false. True, right? False is going to make it false anyway, right? Be careful, all right? I'm glad you try. It's okay to be wrong in the class, right? True. And symmetrically, what's the identity for disjunction? True or false? False, right? Okay, very good. And just for your information, what's the identity for plus? Yep, because 0 plus any number will just be that number. What's the identity for multiplication? 1, right? Adding in, good. Okay, I'm pretty sure you guys know. You just think that's too easy. I'm going to mention that anyway, right? That's how we have the property. Okay, another one that's also mentioned in the slide is called zero property. Okay. Zero, for example, when you have false implies P, that will just give you true. That means it's going to give you some Boolean constant. That means it's always the case, some true over here. Okay. What's the zero of conjunction? That means something here and P is going to give you some Boolean constant, always. But if you put true over here, remember it's going to give you P, right? I think it meant to say false. False, right? Okay, guys, hopefully you see the pattern here. I think knowing the pattern is really important. False here is always going to give you false. And of course, if you prove true here, it's going to give you P. Right? One more. What about the zero of disjunction? it's true, right? It's kind of a symmetric because true equivalent to just true, right? So you really want to think about these two, right? So these are some nice properties just to give you more insight into the truth table, okay? Let's see if there's anything else. De Morgan, there you go. Right, so not P and Q, you just say not P or not Q, and etc. This one is rather easy, right? Double negation, also very straightforward. I listed them just for your information. And contrapositive, right, that's something we just mentioned. Okay, and I think we got 5 minutes. This is one more thing I would like to do quickly. What we want to do here is about predicate logic. Basically, for predicate logic, it introduces two more operators for us to use. Excuse me, universal quantifier and existential quantifier. What I want to do now is to briefly talk about its syntax, 3 or 4 minutes, and then we're done for today. I will continue with it and finish the logic so we can move on to the set. For this course, this will be kind of the syntax you want to get used to. I try to write things in a way you also find very close correspondence to the rodent, okay? And this is universal, and that's existential, right? We'll talk more about their meaning by discussing some example and also proof strategy on Wednesday. But for now, you have to list certain identifier over here, and can be more than one. Could be maybe I, comma, j, comma, k, right? Can be more than one, it's possible. But here I just put one, I just put I here. And the R over here is the so-called range. Okay, the R here is called a range for both of them. I'm trying to compare them at one go. That's the range, okay? And the P over here is the property. So P here is the property. However, the symbols that we use over here, one will be for implication in the case of universal, and this will be conjunction in the case of existential quantification. All right? How do we interpret that? Let me talk about it, and then we're done. The way to interpret this for the first one, for each I, if I satisfies R, the range, which means I is in the range, then P is satisfied. And there is a very implicit but very important case that's not mentioned here explicitly. What if I is not in the range? Then we don't care. It's pretty much like a false implies anything. I'll talk a little bit more about it. But just remember, if I satisfies I, then P will be satisfied. But if there's no such I that satisfies I, the whole universal quantification will just be true automatically. I'll talk more about this next time, but I just want to mention that. Implicitly, if no such I satisfies R, then the universal quantification is just true, because you cannot find any witness of violation. Okay?
Every time I've gotten one, it's been fun.
Sorry?
Every time I've flown into moon, it's been fun, for example.
Yeah, so example, I'm just saying, if the range over there cannot be satisfied by the I, yeah, then it should be true, yes. We will see more example maybe next time. Yes, good, thank you. Yeah, the next one over here, very quickly, and then we are done. Okay, how do we interpret this? For each, oh, sorry, not for each, beg your pardon. There is one I, or there is at least one I such that I is in the range and of course, the n here is corresponding to this, and I satisfies the property P. Okay? And what's really implicit over here? If there's no such I that would be in the range, that means this part over here is already false. Remember the zero of conjunction. That's going to give you false. Right? I'll write it down, and then we're done. Bear with me. Okay, so implicitly, if no such I satisfies or satisfying R, then existential quantification will just be false. All right, guys, I think that's enough. Try to maybe make sure you understand the syntax. So next time, Wednesday, we're going to do some examples, and we'll see proof strategy for these quantifiers. And then hopefully we can move on to sets and relations. Thank you so much. I'll see you on Wednesday. And make sure you start with lab 1.